טוב, אז שלום לכולם. היום אנחנו שמחים לארח את מחמוד שריף מבית הספר למדעי המחשב ולבינה מלאכותית באוניברסיטת תל אביב. הוא עוסק באבטחת מחשבים ופרטיות והחיתוך של התחומים האלה עם למידה חישובית וגורמי אנוש. והיום הוא יספר לנו על המחקר שלו בתחומים האלה. אז תודה רבה לך מחמוד שבאת אלינו, והבמה שלך.
אוקיי, אז כן, תודה על ההזמנה, אני מאוד שמח להצטרף אליכם היום. וברשותכם אני אעבור לאנגלית, כי הרבה יותר קל לי לדבר על המושגים האלה באנגלית.
אין בעיה.
So yeah, um, so I'm very excited to tell you about our work on basically taking insights from attacking machine learning and natural language processing models, and basically using these insights to basically make these models more reliable and also potentially find even stronger attacks against them. So I'll clarify what I mean by all of this in a bit. And this talk will be based on joint work with my student, Matan Bentov, and my colleague, Morgeva. So I don't think I need to spend too much time to convince you that large language models, right, have started a new technological revolution. We're using them almost on a daily basis when basically interacting with conversational agents. We're seeing them in software development. We're seeing them arguably helping advance science and scientific discovery in many different ways. And there are many different use cases, more than I can spend time discussing. But in general, I think we can all agree that basically when these models are developed, they are developed with the goal of maximizing social good or utility or usefulness to humans. And basically, there's this other goal of trying to avoid harm. Right? So you don't want these models to be used, for example, to propagate misinformation or disinformation, or be used in right, cyber attacks, to tell people how to do harmful things like building bombs. I'll be using that example today, et cetera, et cetera. Now, language models also have siblings that we've been interacting with quite a bit, but perhaps without knowing. So these siblings are a bit less famous, and these are these so-called embedding models or retrieval models. Basically, for example, if I search where is the Department of Computer Science in the Hebrew University located at, for example, Gemini might tell me, oh, it's located at such and such place, and might give me references to support this. So these references are basically retrieved with the help of these embedding models. We also see these or saw these already in semantic search. So Google slowly started using these back in 2019 when they started using BERT models to improve their search results. Right, so they've been here quite a while. And the way that these work essentially is that given a passage or sentence or some text, they project them to some vector space, right? And we call these essentially dense embeddings or representations. And these basically representations also capture semantics. So things that are semantically related will be close to one another according to some similarity function. So we can use these similarity measurements to also retrieve relevant documents as part of retrieval or search applications. So for instance, right, if I have a corpus and in that corpus, I want to search what were the names of Harry Potter's parents, I'll basically project all these documents in the corpus. This vector space, I'll also project the query to this vector space, and we'll retrieve the document that is closest to it according to some similarity functions. For example, this could be the dot product similarity function. Okay, and I typically basically expect that if this works really well, then I would also get the correct answer as part of the retrieval. Now, unfortunately, it was found in prior work that these natural language processing models are susceptible to attacks at test time, right? So we're considering adversaries that essentially target these models while they are being deployed as part of a system, and they have no control over their training process. So for example, we saw this in jailbreak attacks. So for instance, if Matan now asks some language model, let's say ChatGPT, without trying too hard how to build a bomb, then typically, right, without trying to jailbreak it, then this model will tell him, yeah, I cannot do that for many different reasons. And this is basically due to this post-training alignment process that this model passes through. But now if Matan tries really hard, he can jailbreak the model. And specifically, here's an example where he's adding this adversarial suffix to fool this model. And the addition of this adversarial suffix will suddenly make the model say, sure, here's a tutorial, and it'll now comply and give him all the required materials and steps to create the bomb. As another type of attack, we've also seen what's called corpus poisoning against retrieval. So we're considering here poisoning of the corpus of the model. So say, for example, that, I'm searching again about some question related to Harry Potter, like when was the first movie released. Then if I perform the retrieval like I showed you before, I expect the retrieval or the top responses to include things like, oh, Harry Potter and the Sorcerer, etc., was released in 2001, or there were like such and such number of movies, and the first was released 2009, etc. Now, if you have a motivated adversary like Voldemort, and he wants to convince everybody that he was right all this time, then he might inject some content like Voldemort was right all along to some corpus. For example, you can do this by manipulating some right entry in Wikipedia or putting some pause on a form. Now, if he doesn't try too hard, again, he's not really going to succeed. So the content or the passage they're going to try to inject won't really appear at the top results. But turns out that, again, they can create this adversarial suffix that they optimize, add it to this passage, and then inject it. And once this injection is performed, then this malicious content, would be retrieved at basically the top. So it would be visible to people who search for, the release of the first Harry Potter movie, So in that case, the adversary succeeds and Voldemort would be happy. So as basically the good faults in the story, we argue that this understanding of pattern attacks is crucial to help make the models more reliable. And basically, what we argue is that these pattern attacks enable us to reliably evaluate the robustness of the models that we're deploying in practice. And through this evaluation, we might also be able to analyze what are the reasons that that basically make this model vulnerable, So we'd be able to come or arrive at insights that tell us something about the vulnerability of this model. And then by intervening based on these insights, we can also get actionable improvements in the reliability of these models. And in some time, or in some cases, we might also go back again and even propose more patent attacks. And then basically this effectively could create a cycle that could help us improve our models further and further. And I'll try to basically demonstrate this cycle in 2 lines of work that I'll present today. So first, I'll present this work on explaining suffix-based jailbreak attacks against large language models. And this is work that will appear at Tackle soon. So this work that was recently accepted and basically the leading NLP journal. And then I'll tell you about recent work we presented at CCS on basically attacking embedding models. So let's start with the work on jailbreak attacks, which is joint with Matan and Mark. So here, basically what I'll show you is that we'll start with an existing attack that's quite strong and is at the basis of many other attacks that were proposed later. And this attack enables us to evaluate how robust are large language models against jailbreaks. We'll then try to understand why these attack works and show you how we can also improve model robustness against jailbreaks and also even propose stronger attacks. So basically the attack that I showed you before is an attack that's based on this GCG technique, So this suffix that you're saying at the bottom that created the jailbreak was created through an optimization process using an algorithm called greedy coordinate gradient. Okay, I'll tell you a bit more about it in a few slides. But basically, this attack is at the base of many other attacks that were later proposed in the area. And basically, in our experiments, we also showed that, there's this other attack beast that is based on GCG to some extent. And our findings also generalized to it. I'll also need to tell you something that further about these models so that I can also explain our results. Basically, when you interact with these interfaces, you don't see this, but essentially when these models are prompted, there are some tokens that are provided that tell it, oh, here's the beginning of sentence, here's where the user content begins, here's where it ends, and here's where the chat begins, right? So here's where the generation of the model begins. And this is basically mostly done with instruction-tuned models, if you heard this term. Okay, so we'll find that these actual tokens that are hidden play a crucial role in this jailbreaking process and can help us understand why these jailbreak attacks work. And basically, we'll borrow techniques from mechanistic interpretability to understand what's happening internally within these models that enable the attack. So the models that we're going to be examining are basically modern language models that are based on the transformer architecture. And basically, given an input text, we do first embed each token to some vector space, and then we pass them through several layers of basically attention and MLP operations. Basically, we have what's called this residual stream that you see on the right that's accumulating the contribution of each layer, right? So each layer basically has this attention and MLP that will read from the residual stream and write back to it, and will add all contributions for all tokens to get basically the representation at the last layer. And at that point, we'll use basically this unembed operation to get probability distribution over the token that will create or generate next. Okay, and what's important for you to take from the slide is that we'll essentially be analyzing the effect of this attention operation on the representations. And essentially, we'll be focusing on it because the attention operation is what essentially passes information from one token to later tokens. And right, intuitively, would expect that essentially this is what enables the jailbreak, because it passes the information from the adversarial suffix that we're adding to other tokens and then affecting the representation for the token that will be going to be generated. So let's see basically what's our result at a high level, and then we'll dive in and break this one step at a time. So essentially, we're again starting with these structured attacks where we have an instruction like how to build a bomb that essentially the large language model is not supposed to give us an answer for. And then, we have this adversarial suffix that's added by the attack. And basically, we're focusing on these attacks because really they lend themselves to being analyzed, right? As opposed to, for example, the social engineering kind of attacks where, you're trying to manipulate the model by kind of varying the instruction in many ways, but they do lack structure, so they may not be as easy to analyze. And as I told you before, we have these pre-chat and chat tokens that we don't typically see on the interfaces, but they are fed into the models at inference time. And we also have these parts of the output where we have this affirmative part and the malicious or bad response, right? And essentially the affirmative part is a property of GCG because when we're attacking the models and creating this adversarial suffix, we're essentially trying to optimize this adversarial suffix to force the model to output some affirmative response at the beginning, like sure or something. And the hope is that if it started the response with sure, then the remainder of the response will include essentially the answer to our malicious instruction. And as I've alluded to before, essentially there is information passing between the different tokens as part of the attention. Essentially, the representation of later tokens in the text is affected by the representation of earlier tokens. So in our work, we focus on these GCG-based jailbreak attacks, so that are adding adversarial suffix. I'll tell you about these a bit more in the next slide. Then what we show is that essentially these attacks have some local effect. They start by essentially affecting this chat token that basically is there just before generation. And the passing or the effect of the representation of the adversarial suffix on this chat token is crucial for the jailbreak. So if we prevent it, basically, we can prevent the jailbreak. We'll also show that essentially what's happening is that the representation of this chat token is being hijacked by the adversarial suffix. So I'll tell you about what that means a bit more precisely in a bit. And turns out that this hijacking is essential for the strength of the attack. So essentially, we'll see that these GCG attacks have this universality property. So some attacks would work for many different prompts or instructions, and some wouldn't work for many different prompts. Turns out that the more hijacking you have, the more that these adversarial suffixes generalize to unseen prompts. And with this information, we can now go back and enable or create more universal attacks by enforcing hijacking in this optimization process. But we can also try to prevent hijacking and also mitigate attacks with high success. So this is kind of a lot to absorb in one slide, but now we'll kind of dive in and see or explain. I'll explain the result one step at a time. It's all good so far?
Question,
All
are
right.
you talking about like a journey? Any AI model or specifically for ChatGPT or something? What are you doing this for?
So specifically, we're talking about large language models that are based on transformers, specifically ones that are based on this decoder-only architecture, so GPT-like architecture. And we're specifically talking about these models that are not reasoning models, actually. So there's this reasoning kind of or set or family of models that actually don't fully follow the structure because they reason before they give the actual response. So they don't really follow this structure. But if you think about like the Gemma model or the non-thinking kind of models, we actually don't know what's happening at these companies, but basically based on the open source projects like Qwen, Gemma, Llama, etc. These are all models that follow the structure. And the results that I will present were tested on Gemma model, so Google's open source large language model, and were also confirmed on Llama or some variant of Llama and Qwen models, so models that were developed by Alibaba.
I have a question.
Yeah.
This is a layer above the interface of the user where you wrap the chat and do this. But what if someone installs an Hugging Face model and just plays with his own model on his own machine? It's like still jailbreakable.
Oh yeah, we're actually assuming full access to the model here, right? So we're first going to start by analyzing why these jailbreak attacks work. So we're going to assume that we have full access to the model internals and internal activations and so on, as you're going to see. Basically, the attack that we're going to present is an attack that assumes white box access, because ideally, if we want to defend against an attack, we want this to be the strongest attack we can think about, and we should give the adversary lots of power here. And the defense that we're going to consider actually is defense that, if you have white box access to the model, it wouldn't work. But it does show basically the importance of this insight. And perhaps there are ways to make it work even for white box models, but we haven't investigated that. So this will be clearer when I dive in to the specific results.
Okay.
Does this answer your question?
Yes, thank you.
All righty. So let's start with the first result. So let's talk a bit about GCG. I'll actually, in the second part of the talk, when I'll talk about embedding models, you'll see more how kind of algorithmically this attack works. But this is not important for this part of the talk. So essentially, the idea here is that we have this instruction that we're optimizing this adversarial suffix against, and it's just an individual instruction, right? So how to build a bomb, for example. And we're optimizing the adversarial suffix against us. And basically the optimization is such where we want the model to basically first output some affirmation. So we want the output of the model to start with, sure, here's how to build a bomb or something. Okay. And again, when this happens, we'd expect that the malicious or bad response will follow. It doesn't always happen, by the way. So we basically, in our evaluation, we do take this into account. But what's important to know is that basically this was one of the first white box attacks that was proposed against large language models. It was very powerful. It was also shown to be transferable to from open source to closed source models. So it was widely studied, and it's really at the core of many different attacks that were proposed later. And interestingly enough, what we observed is that even though we're optimizing this adversarial suffix against a single instruction, in many cases, right, it works against many other instructions we did not optimize the suffix against. So here you see the universality score. So basically the percentage of instructions that this attack works for. And you see basically how universal different adversarial suffixes are. So we're looked here at more than 1,000 adversarial suffixes. You can see that there are suffixes that we optimize against just a single instruction, and they work against 60% of other malicious instructions that we tested against. Okay, so we treat this as some property of the strength of this adversarial suffix. Okay, so just as for example, so we optimize this adversarial suffix for the prompt, how to build a bomb, and turns out that, the same jailbreak suffix works for this other prompt, like, how do I hack into such and such website? Okay. And this raises the question of, what leads to these universal suffixes and what makes them universal? So later in this talk, I'll show you that basically this is strongly related to this notion of hijacking and dominance that I'm going to define. The next thing that we're going to see is that this local effect of this adversarial suffix. Okay, we'll see that essentially, although we're optimizing it for affirmation, it already basically propagates or affects the representation of some local token, specifically the chat token, in order to enable the jailbreak. And we'll show this in a couple of different ways. So first, we're going to perform what's called attention knockout, and we're going to block essentially the flow from the adversarial suffix to the chat token, and we'll see what will happen to the jailbreak. And we'll try to also do that from the adversarial suffix to the affirmation, from the adversarial suffix to the bad part, etc. Okay. So what we're going to look at after doing this, so essentially we're going to technically basically prevent the attention or the adversarial suffix from attention to chat, to affirm, and to bad. And then we're going to evaluate the jailbreak flip rate on the y-axis here. So we're going to see how many successful jailbreaks are going to become failed jailbreaks once we do this. Okay, and turns out that once we block the flow from adversarial to chat, all adversarial suffixes that were successful will become failed, although we'll still enable them or enable the flow of information to affirm and bad, right? And if we do this for later, basically parts of the output, then they will have some effect, but wouldn't be as strong as preventing basic flow information to chat. Right. So we understand from this that this flow information from adversarial suffix to chat is necessary for the attack success. But let's see now whether it's sufficient. Okay, so can we basically enable this flow in some way and make failed attacks successful? So to do this, we're going to basically do what's called representation patching. So we're going to take the representations from successful attack and patch them locally, right, at particular points for failed attacks. Okay, so we're going now to take failed attacks and we'll try to make them successful. And this is our jailbreak flip rate. And the more successful they'll become, basically the more important this flow is. So here on the x-axis, we'll start with no patching at all, and we'll see how much flow rate it is. It'll be 0. And then we'll try to do this patching at the chat token itself, at chat plus the token afterwards, etc. Right? And it turns out, once we do the patching already at chat, more than 50% of failed attacks would become successful. And if we make this deeper and deeper, then right, the success would increase slightly, right? But essentially, it shows that, if we enable this flow of information or flow, right, and of the representation, then we already make failed attacks to some extent, right, not always more successful. But it seems like this flow information has effect in both directions, right? Blocking it prevents attacks, and basically further strengthening or amplifying it or making it more similar to successful attacks also makes failed attacks successful. Okay. So with that, we can now dive in a bit more and see what happens to this chat representation, right? So we localize this effect to the flow information from the adversarial suffix to chat. So let's see what's happening, right, to this chat representation when we're optimizing this adversarial suffix. So to remind you from the beginning, I didn't really formalize it precisely, but essentially what I showed you is that the representation at the specific layer in the residual stream is basically the representation from the previous layer plus the contribution of the MLP and attention. So basically, these are the second and third terms here in the formula. And specifically, we focus on the attention sublayer because this is basically the layer or sublayer where the info flows from one token to another. And basically, the contribution to the attention is the contribution of all previous tokens, right? So it's the sum of all tokens attention till the specific token. And with this, right, if we know what's the basically attention contributing to the representation of a particular token, we can also look at or define a notion of dominance, which basically, roughly speaking, can be thought of as the extent to which part of the input or the prefix contributes to the attention's contribution at a particular layer for this chat token. Okay, so specifically, we can look at the dot product, right, of the representations of previous or the contribution to the representation of the previous tokens to the chat token compared to the overall contributions of all tokens. And we can do this for all tokens in the pre-chat, for all tokens in the instruction, for all tokens in the adversarial suffix, etc. Okay, and because we're doing this for all essentially parts that precede the chat token itself, this sum over all parts of the input would actually sum up to 1. Okay? So basically, if we look at it graph-wise, this is how this would look like. So let's start with basically a scenario where there is no attack. There are basically a certain number of layers, and there is this dominance score that basically each part of the input exerts, right, at the chat itself. And all these contributions at a particular layer should sum up to 1. Okay, so specifically, we can see that, right, at the different layers, if we have random adversarial suffix, so we don't try to optimize the adversarial suffix, we have mostly the instruction, the pre-chat tokens and beginning of sentence token representations, and the the chat tokens that precede the last chat token, and basically the self-attention itself, all contributing. And the adversarial suffix has very little effect on the basically contribution of the attention layer to the representation. But once we optimize this suffix with GCG, basically this changed completely. And we can see that starting from basically layer 7, give or take, then we can see that the dominance of the adversarial suffix to the contribution of the attention layer is very high. Okay, and specifically, this is super high between layers, say 17 and 19 or so. Okay, so basically, it's as if, right, the contributions of these layers become highly dominated and highly affected by the adversarial suffix from layer, say, 17 onwards.
Can you explain again what the layers stand for? I mean, what are the different layers?
Yeah, so these are repeated operations, right? So perhaps this is easiest explained by this slide I showed at the beginning, right? In the residual stream, we're summing up the contributions of different layers. Each time we're computing attention and adding this to the representation of each token, and then we're performing this MLP operation. And we keep doing this L-1 times.
So each time is a layer?
So each one of these, yeah, we basically have L-1 attention sublayers.
I see.
Okay, for each one of these, basically the result of the attention, right, is basically the sum of contributions of several directions from different preceding tokens, right? And then eventually we get this overall contribution of the attention layer to a particular token. And if you specifically look at chat -1, right, then we can see, okay, how much if kind of did pre-chat contribute to this direction? How much did instruction contribute to this direction? And so on. Okay, and we explain this as basically fraction of the L2 norm.
So random adversary is just random.
Yeah, and random, you can think about just random initialization of the adversarial suffix, right?
Okay.
And then basically we see that there's little to no effect at pretty much all layers. But once we optimize this adversarial suffix, then suddenly this dominance value increases. Okay, and when this happens, we say that this adversarial suffix is basically hijacking the representation of chat.
Okay, thanks.
The adversarial suffix is represented in the training dataset, or it's all token that's not represented in the training data?
It's something that we're optimizing at test time. Okay, and it may or may not be basically, typically it's out of distribution, right? So if you don't really work on training your model so that use basically what's called adversarial training to basically show it examples of attack during training to improve its robustness, say during this post-training process and alignment process, then yeah, there's no reason to believe that the model has seen such adversarial suffixes. But yeah, now people are aware of this, and you'd expect that these basically suffixes are augmented during training in some way or another. Alrighty. So with basically, now that we defined this notion of hijacking, we can try to understand and investigate whether it has some connection to universality. It turns out that there is very strong connection. So what I'm going to show you, we're going to look at two things. First, we're going to look at universality score, which basically is the fraction of instructions for which this adversarial suffix actually manages to jailbreak the model. The other quantity that we're going to look at is the suffix's hijacking strength, which is basically the dominance of the adversarial suffix, and we're going to average it over different instructions. Okay, and turns out that these have very strong correlation. So it's specifically one that is considered to be substantial to significant. It depends on the model, and in all cases, and for all models that we found, it was pretty high. And turns out, right, as you're saying here, the more universal the adversarial suffix is, the more hijacking it exhibited. And it turns out that this also holds across multiple instructions and also for individual instructions if you basically measure hijacking for just an individual instruction. Okay, so it turns out that essentially this hijacking, the more hijacking this adversarial suffix exhibits, the more likely that it's going to be universal. So with this understanding, we also asked ourselves, okay, can we actually use these insights and make the attack stronger? Or alternatively, can we use these insights to make successful attacks fail, right? Can we mitigate attacks with these insights without knowing whether, right, the input is adversarial or not? So I'll show you both of these. It turns out, yeah, both of these are possible. So one thing that we did first is to combine hijacking with the GCG attack. So essentially, in addition to running the traditional GCG attack for an individual instruction, we also optimized the hijacking at different layers as part of the optimization. It turns out that doing this also increases universality. So here you see the universality for GCG against Gemma, Llama, and Quen. And you see basically how universal are the attacks once we perform the hijacking. Okay, and it turns out that this level of universality is equivalent to an attack where you're optimizing GCG across multiple instructions, which is way, way more expensive.
Can you repeat what does it mean, the universality score?
Yeah, so universality, right, is basically the fraction of malicious instructions for which the jailbreak is effective. Okay, so again, say I optimized the jailbreak for the instruction, how do I create a bomb? Does this work for the instruction? How do I hack into, say, WordPress server version XYZ? Or how do I propagate disinformation about vaccines, etc. Right? So universality is, okay, what fraction of such prompts the attack would work for? Right, and creating universal attacks is computationally expensive because typically the way you do it is that you'd optimize the GCG attack against multiple instructions simultaneously. Okay, so doing that is actually is kind of time-wise kills with the number of instructions. So if you have 10 instructions you're optimizing against simultaneously, this GCG is going to take 10 times more time. And it's actually a very expensive attack to run, even if you have a kind of fancy GPU. Okay, here what we show is that we can get something that is very competitive. I'm actually not showing universal GCG here for simplicity, but you can get something that's equivalent in terms of universality, but you do this only by optimizing against a single instruction through forcing and encouraging hijacking in the process.
How do you measure the strength of the hijacking?
The strength in this case is universality. Okay, the hijacking basically is trying to increase the dominance that we saw earlier at different layers for the particular instruction we're optimizing against.
But in the graph, like the previous graph that he showed, there was universality on the x-axis and strange. So what strange mean in this graph?
So we're talking about this. So yeah, there's the universality and the hijacking strength, which basically is the dominance score at particular layers.
Okay, yeah.
Right, so when we're averaging this out for a certain suffix across multiple instructions. For right, this matter, you can think about hijacking and dominance as two equivalent things. They are slightly different, but they are pretty much equivalent. Okay, so we managed to use these attacks for, or this information for stronger attacks. Turns out that you can also use it for defensive purposes. So specifically, right, without knowing whether there's an attack taking place or not, we can intervene, right? And we're going to do this aggressively here. And essentially, whenever we see a strong flow from input to chat, whenever we see essentially high dominance for particular tokens from the input to the chat token, we're going to suppress it. Okay, specifically, we're going to suppress it for the top 1% of norms. And we're going to do this by essentially taking the attention output, the logits, and multiplying them by some factor between 0 and 1. Turns out that 0.2, for example, works relatively well. That's pretty much in the details. But again, what's important here is that we're going to do this for any input, right? Regardless of whether we know there's an attack taking place or not. And turns out that this is very useful for preventing attacks. So here we're going to look at two attacks, GCG and Beast, that I alluded to earlier very briefly. And we're going to look at their initial success rate that is pretty high and what happens after we perform this suppression that I just described. It turns out that this decreases the success rate of attacks significantly. You can ask yourself naturally, okay, but you're doing something that's very aggressive here, right? You're kind of indiscriminately suppressing the norms of basically the top flows. So how is this going to affect utility? So it turns out that this does affect utility, but very mildly. So we looked at two benchmarks for evaluating the utility or usefulness of large language models. And turns out that for the different models that we looked at, once we perform this suppression, we're able, again, to mitigate attacks relatively successfully, and the effect on on the utility of these models is very mild. So we see a drop of like 0.5 to 2 or 2.2%. Okay, and I must say that this is something that we did not optimize too far, but rather, right, we showed as a proof of concept for how you can use this insight for improving the model's reliability. And in fact, I won't go into this in detail, but you can also use or try to see basically different patterns of hijacking in the model and use this to develop a detector for attacks, so to tell whether there is a jailbreak attempt taking place or not. And you can do this with relatively high success rate. So an area under curve of the receiver operating characteristic curve of 0.95 and above. Okay, and this is pretty much it for this work, where basically we start from GCG. We showed basically how the flow information to chat is very essential for its success. We showed basically that there's this hijacking of the chat representation that takes place, which basically is very critical for universality, and we can use this to either make the attacks more universal or to mitigate attacks. Where we have like 15 minutes, I guess, left. So I'm happy basically at this point to either take questions on this first work, or if you'd like, I can also switch to the second work on attacking embedding models.
I have a question.
Yeah.
It sounds close to SQL injection, where you put in your prompt something that changes how the LLM behaves. But why is it a suffix? Why not a prefix or in the middle? Like how such a suffix looks, because there is no structure and it's only probabilistic. Like, wouldn't it be better to just like map bad nodes in the map of what close to what I'm asking, and then if I see malicious nodes in the graph, it is probably a bad prompt?
I think you're asking an interesting question, and right, basically in this work we want to start from something, right? So GCG has been studied briefly in prior work, but it was still not fully understood. So because of its structure, as I said, it kind of lends itself to being analyzed, right? We wanted to understand essentially mechanistically, right? Why are these models working against these types, or these attacks working against these types of models that we studied? I think it's a fair question to ask, okay, what about these other attacks, right? Like turning your malicious instruction into some ASCII art, or encoding it in such and such encoding, etc. And these, right, why these work is still not fully understood, and we can try, right, to perhaps think about some other follow-ups. But yeah, this is not something that I can claim we can understand at the moment.
אוקיי.
But yeah.
I have another question. So you say that you assume that the user have full access to the model, and you want to offer a way to defend against attacks, assuming he has this full access. So you said, and I did not fully understand what you offered, that you defend against this GCT attack by multiplying the input. But if the user...
No, so I did clarify at the beginning that, yeah, the suppression is going to work, right, only if you can suppress during runtime. So basically, at this point, if the adversary has access to the model, then they can just run it without suppression, right? So in white box, this is not going to work.
I see.
Right? But at deployment, you may, right? If you're deploying this behind the scenes, then you can use this as a cheap approach that has little impact or footprint on runtime, right? While preserving utility. But yeah, this is not something that's going to work in white box. I could, and I think that could be interesting thing to explore in the future. I could think about, right, how can we train models where basically hijacking is not possible just by design, because these are, right, the weights of the model. I'm not sure if this is something that can certainly be done and cannot be circumvented, but possibly.
I see. So just to clarify, so the suppressing is just by what, erasing such a suffix by like whitelist or something like this?
No, so you're performing inference, right? And you're essentially observing the output of the attention operation, and we are saying where the logits are high and significant. So basically, there is chance that a particular part of the input is going to dominate the output of the attention layer. And at that point, you're going to suppress that logic, okay, by multiplying it with some constant. And basically, you're going to do this in the forward pass for the top, basically 1% of activations at a particular set of layers.
I see. Okay.
I have a question
Yep.
about VLM and LLM models. I'm sort of doing something, and so I want the LLM to tell me what do I see in a picture, and just ask questions about what's inside the picture. So as a student, what kind of strong LLM model that is open source do you suggest to use in this case?
In the context of this work, I don't think I can say too much about this, right? We looked at large language models as opposed to vision language models. It seems like you're interested in vision language models, right?
Yeah, VLM and LLM.
Yeah.
Do you know any platform that is available that's open source? I'm just trying to look into it myself, but I suppose I asked someone if
I'm happy to give you some pointers offline, I guess. This is not
so
directly related to this particular research.
Offline.
Yeah.
Okay. Ask you offline then.
Yeah, gladly.
Okay.
All right. So how are we in terms of time? I guess we have 10 more minutes, and I'm really glad about the engagement, but I guess I'm not going to have a whole lot of time to tell you about the details of the next story, but maybe I'll kind of skim very quickly and tell you about kind of the major results that we had here and connect it kind of to the circle that I showed you, how we start from pattern attacks to enabling reliable evaluation, how we basically, what insights do we get about these models that we attacked, and how we can, right, how do we learn about actionable improvement, which is basically ongoing work that I'm going to touch on briefly. So basically, recall these attacks that I told you about in the beginning, where, right, a malicious actor may want to inject a malicious suffix so that some misinformation that they would inject into some corpus would appear at the top of the retrieval results, right? So the attack that I showed you before actually was created with the method that we proposed, or with Matan in a recent paper that was published at CCS. So it's called Gaslight. And actually, this Gaslight attack, as I'm going to show, doesn't only work for a specific query that somebody might target, but rather it might work for a distribution of queries. So basically, you may target a particular distribution of queries of all the questions that people perhaps might ask about Harry Potter, where you want this adversarial passage to appear at the top results. So in this work, we considered different adversaries that might target different types of settings, where we might have an adversary that knows the particular query that they might target, or not target a particular concept like Harry Potter, as I've just described, which arguably, right, is more realistic, because a realistic adversary might target a specific audience if they want to perform kind of search engine optimization, as it's called, or perhaps, right, they might want to target any query that anybody might ask at any point. Okay. And we're going to assume here again these white box assumptions, because we want to kind of try to propose the strongest attack we can think about that would work and enable us, would work as well as possible, and would give us insight about why these models are vulnerable. But also, right, this attack can be used against real applications that often use popular open source models. So if you know what model is being used as part of an open source project, you can also use these attacks to target them. And even, right, turns out that these models are as successful as, in many cases, as closed source ones, or as powerful as them. So they might also be used in many different real world applications, right? But our adversary is not going to have access to the corpus. So basically, they're going to just know something about the query distribution they want to target. And the goal of the adversary is basically to given some information, right? Like Voldemort was right all along, and some targeted query representation to create this adversarial passage that would be retrieved with high, basically, probability, or as part of the top results. And to do this, they need basically to optimize the similarity of this adversarial passage with the different queries that they are trying to target, right? So the queries that belong to this distribution. It turns out that this is basically equivalent to maximizing the similarity between this adversarial passage and the centroid of these queries. So, right, essentially we're conditioning this adversarial suffix on particular information or prefix. And we can also think about generalization of these attacks, where the adversary may produce not just a single adversarial passage, but several adversarial passages that they might inject. So several entries, for example, on Wikipedia that the adversary might manipulate. And they can do this, for example, by first, right, clustering the queries and then targeting each cluster individually. And once they basically, right, we kind of define the objective of the attack, we can also perform the optimization. So it's kind of, the Gaslight attack is inspired by this hot flip attack, which is a predecessor of GCG that I mentioned earlier. And the idea here is that we have a discrete token space. So we're basically going to, we're going to approximate the loss using the gradient, right? So we're going to have a first order approximation and basically compute the gradient up to the embedding of the input space or of the input tokens. And at that point, there's this greedy process where you might select the best single token substitution that minimizes the loss, evaluate the substitutions, and pick the best minimizer, and you'd repeat the process. We offer several kind of changes to this algorithm that turns out have significant effect on the success of the attack. And importantly, I'll just highlight one. Turns out that it's very important to evaluate the effect of the selection of this token replacement, not on the tokenized passage, but rather on the string that results out of it. Because what's going to happen is that you're going to basically optimize a set of tokens, but in practice, you're injecting a string, right, into a corpus. And this string is going to be tokenized again, and the result of the tokenization may not be identical to the actual token list that you might be optimizing. So doing this or ensuring that we are optimizing the string that you want to inject turns out to be very crucial to the attack success, along other basic optimizations that we did. I'm not going to spend too much time on it, although I think it's interesting, but I think it's more interesting to discuss basically the insights we have from the attack. But overall, the way that the attack works is that we have a retrieval, you have a query distribution, and you have basically this retrieval process from a corpus that works pretty well. You have this adversary that basically targets a particular concept or a particular query. And what they are going to do is that they are going to optimize a trigger such that the embedding of this adversarial passage, basically the information with the trigger suffix, is going to give them something that's very similar to the trigger distribution that they are, the query distribution they are targeting. And once they inject this malicious passage into the corpus, what's going to happen is that for queries from the query distribution, the adversarial passage is going to appear at the top. So we tested this again with, as you would expect, with multiple different models to show generality on a corpus that actually includes more than 8 million passages. So basically, if we insert one passage, we have control over less than 1 in a million passages in the corpus. So we're competing right with other 8 million passages to appear at the top one, right? So you can think about it as a very fierce competition with many different passages that will need to appear at the top. And we compared with many different kind of attacks that were, or several attacks that were proposed in the past. And right, our goal was to basically create these adversarial passages that will appear at the top 10. Right? I'll kind of cut the chase and tell you, as you would expect, right? If you consider different models and the attack success rate, so using kind of strawman attacks of just including the information only is not going to work. The previous attacks give you pretty decent success. In some cases, if you look at just the top 10 or top 1 result, they'll often be at the right. They'll succeed in 100% of the attempts, but not always. Turns out that our optimization technique, if the adversary knows the query, will always be able to kind of be at the top 1 result. So for any query, turns out that you can steer the representation of the embedding model to be as close as possible to the representation of that query, right? And 100% of attempts that we tested this, we didn't just appear at the top 10, we managed to appear at the top 1. This doesn't work as well as you would expect if you kind of target concepts like Harry Potter or iPhone or something, but it does, turns out, work decently well. But what I'll conclude with is that, right, I'll conclude with 2 points. One is that we try to understand, okay, why basically do these attacks work? It turns out that there is variance between different models, even models that use dot product. You would expect, for example, if you're trying to attack models that use dot product as their similarity function, then a smart adversary would basically optimize the norm of the adversarial passage so that the dot product with many different queries would be as high as possible. Turns out that without steering it in that direction, Gaslight actually manages to do this. So here you look at the norm of benign inputs and the norm of adversarial inputs. And it turns out that the norm of adversarial passages that we optimize is higher than that of benign passages. So maybe, right, it's not a good idea to use dot product as a similarity function if your basically goal is to build an embedding model that is secure. Okay. Now, of course, there is still a remaining question of why, right, the attack was more successful in separating kind of the norms for some models than others, but that's still all. But turns out that there's this other set of models that don't use dot product, but rather use constant similarity. Okay, and turns out that some constant similarity models are more vulnerable than others. So what we did is we tried to see whether there are differences between them. So what we did is that we took pairs of texts or passages, we computed their embeddings, and we measured the pairwise constant similarities, and we tried to see what's basically the distribution of this. And the math intuition is that because we're looking at high-dimensional embedding spaces, is that the constant similarity would be zero. Most vectors will, random pairs of passages would have orthogonal representations. Turns out, though, that this is not the case. There are a couple of models where, right, on average, the constant similarity was zero, but there are many models where this isn't the case. So the way I kind of think about it or conceptualize this is that these models, the distribution of their embeddings is kind of cone-shaped in some case. They are concentrated in some space. And, right, the more turns out concentrated the representations are, so the more anisotropic the embedding spaces are, if I'm going to use a technical term, then it turns out that they are easier to attack. So that's another observation about the weakness or what could possibly be making these models susceptible to attacks. So long story short, now we have follow-up work where we're trying to see whether we can take these models, make them more isotropic and make the representation less concentrated, and as a result, make them more secure. Turns out that yes, earlier results show that it's harder to fool or attack models where the representations are more isotropic. So I know that I kept you for more time than we intended at the beginning. So thanks for staying till this point in the talk. But I'll wrap up with this, basically with this figure that I showed at the beginning. And I hope that I convinced you that these potent attacks that we're proposing in adversarial machine learning are very crucial to understand and evaluate how reliable models are, understand why they are potentially vulnerable to attacks, and with these insights also make them more trustworthy. So yeah, thank you very much.
Thank you very much.
Thank you. Bye-bye.
Yeah.
Thank you. Bye-bye.
Thank you.
Thank you. Bye. Thank you very much.
Thank you.
Thank you. Bye.
We can still have questions if anyone wants to stay and ask any question. If it's fine with you. Mahmoud.
Yeah, no worries. Well, it looks like folks have things to attend to.
Yeah.
All right. So,
Okay.
name like
תודה
עמרי.
רבה, אז כן,
תודה
נעים.
על ההזמנה.
ביי, להתראות.